Alright, on today's lesson we're going to be talking about the force of gravity experienced between any two masses. Before I get into that, I just wanted to go over this data table. So this is a really useful data table. It has some constants, it has some prefixes, and it's got some information on our solar system. So one thing that I want to highlight here is the gravitational constant. This is constant for the universe. It's represented with a large G, and it's 6.67 times 10 to the negative 11, so it's incredibly small, and then newtons times meters squared divided by kilograms squared. The units seem a little unintuitive or a little crazy, but this is used so that when we use it in our equation, all the units kind of work out and cancel out the way we want. We got some metric prefixes here that I'm not going to spend too much time on. And then this is a solar system data table. So I have the masses of all the different planets. We have the radius of the object. So this is the actual radius of the planet or of the sun. And then the orbital radius. This is the distance between the planet, the center of the planet, and the center of the sun. Okay, that's orbital radius. And orbital period tells you how long it takes to go once around the sun. Now for Moon, the orbital radius and the orbital period are that of how long it takes to go around the Earth, not around the Sun, seeing as the Moon is orbiting the Earth. So you'll be using this in some of your questions. So this lesson is talking about gravity near the Earth's surface. Now for the most part, we always just assume G is 9.8 meters per second squared downward, which is correct as long as you are close to the Earth's surface. So close, I mean like within 100 kilometers or so. As you get further than that, the distance is so great that the G, or like the acceleration due to gravity, actually decreases. So it is relatively uniform near the Earth's surface, but the further away you get from it, the smaller it becomes. And any two masses are related in this equation here. So I have my force of gravity between the two masses is the gravitational constant G times one mass times the second mass, and then divided by the radius squared. Now, other ways of writing this is my gravitational force is my gravitational constant, and then my mass of mass 1, my mass of mass 2, all divided by the radius between them squared. So notice on this equation here that my gravitational force is proportional to my mass, right? If I double my mass, I double the amount of force, and that's for either of the masses. And also notice that my force of gravity is proportional to 1 over the radius squared. So what that means is if I double the radius, I actually decrease the force by a factor of 4, or 1 over 2 squared. So pretty much the tighter the mass is, the smaller the radius, the more the force is going to be. So another thing to note here, on this one equation, m subscript e stands for the mass of the Earth, and the radius is the distance from mass center, so it's the center of the two masses to the Earth, and I'll show that in the example coming up here as well. So we can find the acceleration due to gravity for any planet using this equation. So if we know the planet's mass, we can actually figure out what its acceleration due to gravity is. We need to know its mass and the radius of the planet. So for a body close to the Earth's surface, I know that the force of gravity is equal to mass times gravity. But here, I am going to equate this is also another way to say the force of gravity. So I'm going to move this in for here. So notice I have mg is equal to big G and then the mass of the Earth times the mass of the object divided by the radius squared. And when I do that, I have a small mass on both sides, so those will cancel. And the G, or the acceleration due to gravity for any planet, can be found using this equation. So we know our gravitational constant G from that data sheet, and then the mass of the planet, or me, is the mass of the Earth, divided by the radius squared. And that is the distance between the objects. So For an object near the Earth's surface, it's reasonable just to use that the radius is equal to the radius of the Earth. So, you know, when we're close to the Earth's surface, we just use g as 9.8 meters per second squared, but that isn't always the case. So a couple things to notice here is that g is independent of the mass. It only depends on the mass of the large object. And it's approximately constant near the Earth's surface, but not always. So we usually use 9.8, but today we're not going to. So here's our example. It says find the acceleration due to gravity 100 or 1,000 kilometers above the Earth's surface. So the total radius, if this is my Earth here, this blue ball here, if this is the Earth, this is the radius of the Earth here, and then I'm adding this 1,000 kilometers on it. So my total radius is going to be the radius of the Earth plus 1,000 kilometers. Now I want all this in meters, so I looked up on my data sheet what the radius of the Earth was, and I got 6.38 times 10 to the 6 meters, and then I added in my 1,000 kilometers, which is you know, 1,000,000 meters. So I added those together. So this is my new total radius here. So that's the radius I'm going to use in my equation. Then to find g, I used that equation earlier in the lesson, which was the gravitational constant times the mass of the Earth divided by my radius squared. And I sub everything in. I dropped the units here when I was doing this. Again, I got the mass of my Earth from my data sheet. I get all this, and I multiply it all together, and I get 7.32 meters per second squared. So you'll notice it's less than 9.8. So the further off the Earth's surface I get, the smaller the acceleration due to gravity. So you can represent it as meters per second squared or newtons per kilogram. And note that meters per second squared and newtons per kilogram are equivalent units. So as you get further off of the Earth's surface, g changes. So you can't just use 9.8 the whole time. And then I made up another question here. It says, example 2, you are an 80 kilogram astronaut curled in a ball, okay, with a radius of 0.25 meters. And then I'm saying calculate the acceleration due to gravity that the astronaut would have if the astronaut was like, he pretended he was like his own little planet or his own little asteroid. So here, I use the same thing, gravitational constant. Rather than the mass of the Earth, I use the mass of the astronaut as 80 kilograms. And then the radius of him is only 0.25. Anyways, when you do this, you get a ridiculously small number. Like, it's almost like you have no acceleration onto yourself. But it actually isn't zero, right? There is a value here. It's just really, really small. So it was 8.54 times 10 to the negative 8 meters per second squared. So for the most part, we assume like the attractive force between you and, let's say, the computer in front of you right now, it feels like zero. There is actually an attraction there. It's just so much smaller than the attractive force between you and the Earth that we assume it's zero. But when we're dealing with some astronomy and space things, we have to actually work with those numbers too. Again, thanks to Mr. Smith for producing these great worksheets that we're using in these videos. Alright, I'll pause it here and then we'll go into low Earth orbit in a sec. Okay, let's talk about a low Earth orbit here. So Newton did a lot of experiments, both physically and even just mentally. So this is a thought experiment that he did. He says if you drop a stone, it falls in a straight line to the ground, kind of like you can see in that first picture below, right over here. If you throw a stone horizontally, it'll follow a curved path or a parabola. If you throw the stone faster, it'll land farther away. And the curvature of the path will be less pronounced. Now his thought experiment was, what would happen if the curvature of the path, so this curvature here, what if that curvature matched the curvature of the Earth? So the stone is falling at the same rate that the Earth is curving. Well, then the answer is, in the absence of air resistance, the stone would move in a circular path around the Earth. So an orbit is you launch something hard enough off of the Earth that it's constantly falling, but it's never hitting the Earth again. It just goes around and around and around and around. So his next question is how fast would the stone have to be thrown horizontally in order for it to enter Earth's orbit? Well, it depends on a few things. It depends on the rate at which the stone falls, so the acceleration due to Earth's gravity. So thinking back to our projectiles and free fall stuff, if we drop a stone from rest, it accelerates at 9.8 meters per second squared. So how far will it fall in a second? Well, if my initial velocity is 0, I can use this equation from my kinematics unit, and I sub all my info in there. So 1 second of falling, it will fall 4.9 meters, roughly 5 meters. Okay, and this is the same if you launch it horizontally. Remember, the x and y components for projectiles aren't actually related. So if I drop it, it goes down 5 meters in a second. If I throw it sideways, it goes down 5 meters, etc., etc. So next page says here, the Earth has a geometric fact that the curvature of the Earth is such that it drops a vertical distance of 5 meters, or 4.9 meters, every 8,000 meters to the side. So if you go 8 kilometers sideways, the Earth curves 5 meters downwards. So if we can shoot something sideways at 8 kilometers per second, which is incredibly fast, but if we can shoot it sideways at 8 kilometers per second, it's going to be falling 5 meters per second, and it will follow the Earth's curvature. So this would be how fast you need to launch something in order for it to enter into orbit. So we said low Earth orbit for Earth is approximately 8 kilometers per second, or if that's in kilometers per hour, that'd be 29,000 kilometers per hour, which is incredibly fast. But motions of planets and satellites also kind of match this. So a satellite is put into orbit by accelerating it to a sufficiently high tangential speed, or sideways speed, so of about 8 kilometers per second, and that's with the use of rockets. If the speed is too high, it'll kind of skip off and not orbit the Earth, and if it's too low, it'll fall back in. So for this, for something going around a planet, so if I have my planet here, if I have my planet and the object is moving around like so, my centripetal force, so my circular motion force, is going to match my gravitational force. And then I sub in my equations for both of those. Well, I know my centripetal force is mass times the velocity squared divided by the radius, and my gravitational force is my gravitational constant, mass of the Earth, times the mass of the object divided by the radius squared. And then I can do some canceling. Notice I have mass on both sides. So if I divide both sides by mass, those go away. And I solve for velocity. So if I multiply r on both sides, this one goes away too, and it'll get rid of one of the squareds. So my velocity squared is equal to my gravitational constant times my mass of my Earth divided by the radius. And then I take the square root of both sides to get this one here. So this is the minimum velocity I need. And this is called the speed of an object in a circular orbit. So this is how you can calculate it. You know the mass of the planet, you know the radius, which is the distance from the center of the planet to the satellite, and the gravitational constant. So a couple of notes here. We can use this result to find an orbital period of a satellite, since we know that the velocity of the satellite is the circumference over the period. And you can actually use this equation to find any object in orbit around another. So the mass of the central body would just replace the mass of the Earth in this equation. So if you have something orbiting a different planet or something orbiting the sun, whatever the object is orbiting around would be the mass of the large M in this equation here. And the third point is r is not the radius of the Earth, it is the Earth's radius plus the altitude of the satellite's orbit. Okay, so let's try an example here. It says here a satellite in low Earth orbit is 225 kilometers above the Earth. What is its orbital velocity? So first things first is my radius for my equation is going to be my planet radius plus my altitude. I got my planet radius here from my data sheet, my data table, and my altitude is 225 kilometers, or 225,000 meters. And then I use this equation here. which was from earlier. So I take the square root of my gravitational constant, mass of the Earth, divided by the radius, which I just calculated from here, and I do all of that, and I get it is traveling sideways at roughly 8 kilometers per second, or 7.771 meters per second. So that's really, really fast. And then it says, what's the orbital velocity? Well, this is my orbital velocity. Now, it doesn't ask for this, but I'm going to find out the orbital period. Okay? So my velocity is 2 pi r times divided by my period. So I rearrange this equation. I multiply both sides by period, and then I divide both sides by velocity, and I get period is my circumference, or my distance, divided by my speed. So, again, my radius is what I calculated from earlier. I put it all in, and I get a period of 5,340 seconds, or 89 minutes. And this isn't just a made-up physics worksheet. This is actual numbers and data from our planet. So the orbital period for something in low Earth orbit is 89 minutes. So something like the International Space Station goes once around the entire Earth every 90 minutes. So if you're an astronaut on the space station, there's like a 90-minute day-night cycle. So like every 45 minutes it's day, and then the next 45 minutes it's night, and then the next 45 minutes it's day, and you keep going like that, which is really fast. So if you ever look up in the night sky and you see something going across the night sky really quickly, odds are is that is a satellite in low Earth orbit. And there is actually an ever-growing number of satellites in low Earth orbit. Now, the object that has the longest period going around the Earth has the greatest distance from the Earth, and that is the Moon. The Moon is very, very far away. So because the radius is so large, the velocity it's still pretty big, but the period is much smaller. So the period that it takes, the amount of time it takes the Moon to get around the Earth is like 28 days. So if we had a satellite that far out, it would take 28 days as well to get around once of our orbit. All right, so Mr. Smith again made this great worksheet, so thank you to him. There's some good questions here as well that go over this. That data sheet is required to answer some of these, so make sure that you reference that to get your info for this. But yeah, we'll leave that here for this lesson as well.